So let's put the lights down, because I've put a light on the end of the pendulum here. Okay, here we go. It's alive! It's just going to keep going. Alright, it's gone back to swinging now. It loses energy over time, so it goes back to swinging. I'll do it one more time, because it really is good. Honestly, I could watch this all day. Well, thank you very much. Good night. It's hard to follow that. I love this thing, but it's demonstrating something that crops up all over physics. It's demonstrating this motion that seems so unpredictable. This is known mathematically as chaos. And we find it all through physics, but the first person to spot that this might happen was in fact Henri Poincaré. When he was thinking about the solar system, he realized that motions within the solar system could be chaotic, which isn't really our normal way of thinking about the solar system, because normally we think, well, there are all the planets there and they're feeling the pull of the sun, and that's keeping the planets from flying off, and it's all fairly predictable. But what Poincaré realized is that you have, every now and again, a little kick as two planets come close to each other, because this gravity force that's pulling the planets towards the sun is also pulling all the planets towards each other. Although that's quite weak, because the planets are small compared to the sun, over time the effects can build up, and a little kick now and again over a whole billion years can build up into something that's really, really hard to predict. And in fact, Poincaré said it's impossible to predict, and a bit later on I'll show you why he thinks it's impossible to predict and why we still think today it's actually impossible to predict. But I want to show you more in space. I mean, this stuff doesn't just apply to the solar system and to pendulums. We see it throughout space, and to show you it applying elsewhere in space, I need to show you what's in space. If you look up to the sky in a dark place on a dark night, and you have sort of normal vision, then you'll see maybe a couple of thousand stars. But if you've got a telescope, you start to see there are far, far more things than you can actually see. The things that you see are just the nearest and brightest stars, the A-list stars, if you like. The night sky itself is actually crammed with far more than that, much more distant stars and dimmer stars and gas and dust. And it's quite hard to see that with your naked eye, but if you have a telescope, then you start to pick it up. And our best estimates today say that in our own galaxy there are something like a couple of 100 billion stars in total. So our galaxy really is crammed with stuff. But that's not the end of the story, that's not the end of space. If you know where to look, if you've heard of something called the Andromeda constellation, and you look at the Andromeda constellation on a really dark night, then as well as stars, you'll also see a faint smear of light. It's about the size of the moon, but it's just a faint smear of light. And here is a picture taken with a telescope of that faint smear of light, made to look quite nice and bright so we can see it properly. And this smear of light is actually another galaxy beyond our own. It's called the Andromeda Galaxy. And it seems that that also has about 100 or 200 billion stars in the Andromeda Galaxy. And that's not the end of the story either. In fact, a few years ago, astronomers took the Hubble Space Telescope, which is an incredibly sensitive instrument, and they decided to point it at a tiny patch of the sky, maybe about 1/10 of the diameter of the moon. And that patch of the sky was thought to be completely blank. And if you take something that's really sensitive and ask it to point at something that's tiny and completely blank, then what happens is it says, well, that's just ridiculous. Look, I took this picture, and I took this picture, and I took this picture, and you want me to point at something that's completely blank. Well, all I'm saying is, no, it's fine. No, obviously you're in charge, you're the astronomers. No, it's absolutely fine. If you want me to do it, it's fine. But all I'm saying is, when we get back into the boardroom, if Alan raises this, if he says, then I'm not taking responsibility. I've already told my talents lie in taking pictures of things, not in pointing at blank bits of the sky. But anyway, once they'd finished having their little tiff, the astronomers won, and they got the Hubble Space Telescope to point at this bit of the sky. And over about a week, leaving it pointing at that same bit of the sky, this is the picture that built up. It's not blank at all. If you stare at it for long enough and collect as much light as you possibly can, you find it's actually crammed with stuff, just in that tiny patch. And every dot of light in this picture isn't a star, it's another galaxy, all in that tiny amount of space. So if we take that and imagine that we could search over the whole sky using Hubble to find all the galaxies, there's no way we could do this. It would just point blank refuse to do it. But if you could, then we think you'd find at least 100 billion galaxies in the universe, each with their own 100 billion stars. So the universe has got quite a lot of stuff in it. But we're still not done yet. Because suppose we go to just one of these galaxies. I could have picked any one, but I picked this one, happens to be called the M81 galaxy, catchy name. And we try and work out, well, how much stuff is actually in this galaxy? Well, there are a few different ways you could imagine doing that. The obvious way is just to see, well, how much light is coming from the galaxy, and from that you can go, how many stars must there be? And you can get a bit more detailed. You can say, well, what are the colours? Is the gas in there? And you can just see, what can I actually see there? And make an estimate of how much stuff you think is there. Lots of people have done that over many years. We're now very good at trying to work out how much stuff there is in a galaxy. That's where these numbers of, 100 billion stars and so on come from. But there's another way that you can find out how much stuff there is in a galaxy. It turns out that galaxies are spinning. And they're spinning for the same reason that the Earth is going around the Sun. It's because of gravity. So if you measure how fast a galaxy is spinning, then that tells you something about how strong is the gravity within that galaxy. And if you know how strong the gravity is within a galaxy, then you can say, well, how much stuff do you need to make that much gravity? Because gravity is just generated by stuff. The reason we feel gravity here on the Earth is because the Earth is so big and it's creating gravity, and the Sun also is creating gravity and so on. So you can work out how much stuff is there just by going through how much gravity there seems to be. Now, it just so happens that when you do this, for every single galaxy we've done it for, the numbers just do not agree. When you do it using the spinning method, you find an answer that there's 5 times more stuff than the stuff that we can actually see directly. In other words, 6 times as much stuff in total. And because we haven't got a clue what's going on, we invent a cool name for the extra stuff and call it dark matter. The thing about dark matter is it's not just in galaxies that we find it. If we go to a cluster of galaxies, so this is, in the universe sometimes you don't just find a single galaxy sitting there on its own like the ones I've shown you so far. Sometimes there are lots of galaxies that are close together. When that happens, gravity gets very strong indeed, and it actually starts bending light. So we normally think light travels in a straight line, but when gravity is strong enough, it can actually pull light round in the same way that stuff like us, pull down towards the Earth. Light can actually be pulled around by gravity as well. So, if you go to something really big, really heavy, like a cluster of galaxies, that starts to happen. You can actually see that the light has been bent in this picture. And then you can do the same trick. You can say, well, how bright is all this stuff? And from how bright it is, you work out how much stuff do we think is there. And then you can measure how bent all of these images appear. And from how bent it is, you get how much gravity there is. And from how much gravity there is, you get how much stuff there is. And you end up with the same answer, that there seems to be 5 times more stuff in what we now call dark matter than there is stuff that you can see directly. And these are the kind of things that have convinced us that dark matter exists. So now I want to check with you. Do you believe in dark matter? Yes. Oh. I actually, in my notes, I put the audience will be friendly but skeptical. So that's a failed prediction, right? Perhaps so, just to keep it on track, maybe you could be friendly but skeptical. I try again. Do you believe in dark matter? Oh, you sound a bit skeptical there. But I have to tell you, in a sort of off-the-cuff joke moment, I have to tell you that 5/6 of the audience are very convinced. It's just that you can't see them. So now that most of the audience is in fact convinced dark matter exists, we can start asking things like, well, what is it made of? If there's extra stuff out there that we can't see directly, we'd really like to know what it's made out of. And for inspiration, we turn to the familiar world around us, the world of, desks and seats and floors and lights and the sun, and things that we understand pretty well. And what we know about things like that is that if you zoom down, if you look closer and closer, you get a big microscope, really good microscope, you look on a smaller and smaller and smaller scales, eventually you find everything is made out of what we call particles, which are just sort of tiny chunks of stuff that we can't actually divide up any further. And as far as we know, all matter is made out of these particles. So we go, well, I suppose dark matter must be made out of particles then. We could call them dark matter particles. It sounds nice and technical. That's literally the level of thought that's gone into that bit. But then, of course, we want to know how do dark matter particles behave? And again, we look at the familiar world around us. We say, well, what do we know about the particles that we're used to? And the main thing that we know about particles is they feel forces. So, for instance, why am I attracted to the Earth? It's because all of the different particles that make me up are pulled down by the force of gravity towards the Earth. And then you can ask, well, hang on, why don't I fall through the floor if I'm being pulled down towards the centre of the Earth? And actually, we think that's because of another force. I don't really have time to go into it today, but there's a force called electromagnetism. And when I stand on the floor like this, the only reason I don't sink through it is because there's another force pushing up on me where my shoe is making contact with the ground that comes from this electromagnetic force between particles. And that's why we don't fall through things. Now, it turns out that electromagnetism, the electromagnetic force, is also the reason why we can see things. Light itself is a sort of aspect of that force. So when we go over to dark matter particles, we go, well, all right, they've got to feel gravity, right? They've got to create gravity and respond to gravity, otherwise they don't do the thing that we invented them for. But, on the other hand, we can't see them. So that probably means that they don't feel the force of electromagnetism like we do. And that is pretty much as far as we've got with working out the properties of dark matter. We haven't got much further than that. But it does allow us to work out some pretty fundamental things about dark matter, like where is it in the universe? I mean, for a really convincing demonstration that dark matter definitely exists, I think the best thing we could do is actually find some. actually get our hands on some. And we can make predictions for how much of it is, say, in this room. If you wanted to build an experiment that could actually find dark matter, the first thing you'd want to know is, well, how much is in this room? And you might think there'd be quite a lot. After all, I did say that there's 5 times more of this stuff than there is of the familiar matter that we're actually made out of. But actually in this room, you'd be wrong about that. Because the Earth is formed out of normal matter, and what's really important about that is these extra forces that I've been talking about. So if you imagine in the early days before the Earth existed, there were just lots of bits of rock and dust strewn about. And then what happens is that rocks can sort of bump into each other, and when they do bump into each other, they're a bit sticky, so they kind of stick together, and more dust comes on, it all sticks together, and it gets bigger and bigger, and eventually you're left with a big lump of rock, and that's the Earth, and that's the limit of my knowledge of geology. So, are there any geologists in? There's a geologist at the back. Would you agree that's pretty much all you need to know about geology? Yeah, she's nodding. That's all you need to know about geology. Good. So that's dealt with geology. So the reason that there's so much stuff, normal stuff, here on Earth is because stuff is sticky. Dark matter, we think, can't be sticky because it doesn't feel any of these forces. It needs to be sticky. So although there's 5 times more of it on average, here on Earth we've got a big lump of normal stuff. So actually that means the normal stuff can outweigh the dark matter by quite a lot. So if our calculations are right, then in this room, right at the moment, what's happening is that dark matter particles are arriving. So they're coming from the northwest, which I think is over. This depends on the time of day and the time of year, by the way. But right now, I think they're coming from the northwest, which I think is probably over there, quite high up in the northwest at this time of day. And they're coming at 100 kilometers a second. That's pretty fast. And because they don't feel anything, so they're streaming at us from space. They're coming through the ceiling without noticing it's there. They're going through your head, through the seats, through the floor, through the whole Earth, and out the other side of the Earth. So can anyone feel the dark matter? Are you sure? I think that wasn't really what I was expecting to happen. I'm not sure what the correct response to that is. No, of course we can't feel the dark matter normally. The reason we don't feel them is to feel anything there needs to be a force there. The reason I can hurt myself, the reason I hurt myself on the pendulum earlier on, is because of the forces. And there isn't a force there to do that. And so it can just come through, it disappears. But if you could somehow freeze time, that just totally destroyed that. You just ruined that. Oh. If you could freeze time and search throughout this room, find all the dark matter, we think there'd be something like 1 million particles of dark matter in this room with us right now. And that sounds like quite a lot, but actually particles are very, very tiny, so that's actually just 1 millionth of a millionth of a millionth of a kilogram in here. And at this point, you might be wondering, well, how on earth do you go about finding 1 millionth of a millionth of a millionth of a kilogram of something that's invisible and untouchable? Which is a great question that I'm not going to answer. You can ask it later on, and I can try. But there's another question here, which is what I really want to focus on to get back to the pendulum, which is how on earth do we know, how on earth have we made a calculation of how much dark matter is in here and how fast it's coming through and from what direction? Now we can do this using computers, and I'm going to show you one of our computer simulations of the way that dark matter works. I'm going to show you it in a very particular way. What I'm going to do is I'm going to take a virtual galaxy. So we've got a galaxy inside the computer, And what the computer is able to do is calculate all the gravitational tugs that all the different bits of the galaxy are exerting on this one blob of dark matter that I've labelled there. So that we can find out, if I just drop a blob of dark matter into a galaxy and it feels all this gravity coming from all the different bits of the galaxy, what happens next? This is all, of course, on the assumption that we're right, that gravity and no other forces are applicable for dark matter. But we can do it nonetheless. And we use computers because they're required to add up all these different forces and get us a sensible answer. So this is what happens. There it is. It's attracted mainly towards the centre, where most stuff is. So you'll see it keeps going through the centre. But it sort of swings back and forth, because by the time it gets to the centre, it's got quite a lot of speed built up, so it just kind of flies through and comes out the other side. Now, what you might have noticed about this is that it looks pretty unpredictable. It looks chaotic, in the same way that the motion of the pendulum looks chaotic. And in fact, mathematically speaking, it is chaotic, which means it's very hard to predict, because it changes its behaviour quite wildly from one moment to the next. And what's really unnerving about this, if you care about making predictions for what happens to dark matter, is that I can sort of do this experiment twice on two different computers. Now, for the experts, I'm using 32-bit precision on the left and 64-bit precision on the right. You can just think of it as like PC and Mac if you prefer. These are just two different computers given exactly the same piece of computer code and asked to solve exactly the same problem. And I'm just going to show you what happens when we set them going. So at first, everything looks fine. The dark matter goes round sort of the same, and it's looking a bit boring. But if you watch really carefully, you might start to notice there are slight differences between the two sides. I don't know whether you can see that. And over time, those differences get bigger and bigger, until eventually, the thing on the right is doing something that is just completely different from the thing on the left. And that's kind of worrying, because we've got two different computers and they give us two different answers to our question about what dark matter is doing. Now, to understand the reasons for this, you can just launch a calculator app or something, if you've got one on your phone. You can calculate along to this, by the way, if you want to have a go. It's fun for all the family. If you open a calculator app and type in 1.234, this is a very serious calculation, 5, 6, 7, 8, 9, and you divide it by a billion. So divide it by 1,000,000,000,000 American billion, and then multiply it by a billion, 1,000,000,000,000,000. You should get back to what you started with, but you don't. Right? You started with 1.2345678, and you end up with 1.23457. Computers are rubbish. The one thing they're supposed to be able to do is numbers, and they can't. And you might think, well, that's okay, because, you know, you can just increase the level of precision. Because what's gone wrong here is that the computer's just not storing the numbers accurately enough. It's not keeping a record of these numbers accurately enough to be able to go back to what you first started with. So you might think, well, yeah, that's okay. Well, we just need to turn up the precision. In fact, that's what you do when you go to 64-bit. You're just making it more precise. But the trouble with that idea is that then, if you go to an even better computer that's got 128 bits, then you find it's completely different again, what this dark matter ends up doing. And if you go then from 128 bits to 256, it changes again. And that is what Henri Poincaré realized would be true of the solar system. It doesn't matter how accurately you try and keep track of all the numbers you need to work out what's going to happen to the solar system. Your calculation is going to go wrong, because you would need an infinite number of digits on your numbers in order to get this right. And for a start, nobody can measure the position of everything in the solar system to an infinite number of digits. And secondly, it would just take too long to write any of them down. And now, we're seeing it elsewhere in the universe. We're really serious about trying to make predictions about dark matter, and yet the computers kind of scupper us. The computers just are not good enough to be able to do that. And the real thing is, the computers are... Sorry, it's, that's not meant to happen. It's a... So, what can we, I'm not sure. Right, okay, that's... Oh! Yeah, no, that's what I thought it would complain about. Right, later on, I'm going to be giving you a memory card with some pictures on. You can import them into iPhoto if you like. When I said it was sensitive, this is not what I meant. It's a brand new 64 gig memory card with extra speed. All right, should we do that? Is that all right? Right. Good. Well, that's that out of the way. Where was I? 32-bit, 64. Yeah, right, okay. So, the problem that we've got is that these systems that we call chaotic, are just far too sensitive to what we do. I mean, every time I start this pendulum, it does something slightly different, because I just can't start it accurately enough in the same way. And the same problem applies to dark matter. If you just lose the tiniest bit of accuracy on your calculation, it ends up doing something completely different. And this is a massive problem, right? How can we possibly claim to be able to calculate what's coming through this room at the moment if we can't work out what happens to a single blob of dark matter? Now, to answer that, I've actually invented a brand new experiment to show you how this works out. This is called, wait for it, this is going to be the world's first long exposure selfie. Alright? This is going to be worth it. I'm going to take this is just a normal camera, and it's got a long exposure mode where it's able to keep recording the light that's arriving at it for 20 seconds is what we're going to do. And that's going to help us keep track of exactly what this pendulum does over quite a long period of time, 20 seconds. So I'm going to give this a go. I'm going to stand next to it at a safe distance, and if we can have the lights down again, then we will do the world's first long exposure selfie. Here we go. Right, it's just twizzling round at first, but of course when it loses a bit of energy, it's this is a selfie. – 20 seconds is quite a long time, actually. Maybe I should do less. It's a very long time. Okay, that was it. You just witnessed it. Now, if I take out the memory card so that we can see what we've just recorded, I'm just going to pop it in here. There we are. Okay. Oops. Here is... Oh, it's good. It's good. There it is. Now you can see one thing has gone slightly wrong with this, in that the right-hand side looks very dim. That's slightly unfortunate because it makes it look a bit harder to look at. It's actually because we tried to get this sorted out, but clearly not. It's actually because the LED sometimes looks a bit dimmer on this side of the camera than on that side of the camera. But nonetheless, so if you slightly ignore that, you can see the kind of patterns that it's made. Now, the thing is that we can actually understand quite a lot of these patterns. Although the specifics of what happens when we set this thing going are quite complicated. You know, the actual path it went through looked very unpredictable. There are certain things when you look at it like this that you can predict. So for a start, you've got the fact that at the top here, there's not very many lines that are going through the top. In fact, if I go all the way up here, you can see not very much up there. Another thing you can see is that it never goes outside this circle, right? Never outside there. And the final thing you can see is it tends to come back towards the centre quite a lot. If you look over here, it's coming back towards the centre quite a lot there. And we can actually understand all of these features. So but you know, why is it that it never goes outside a circle? Well, that one's pretty obvious. It's because this thing is only a certain length. So if I take it round, you know, it just cannot get any further unless the thing flew off and hit me in the face, but that would not be good. So that's what means that it's got to be within a circle. So that's the first thing we can understand. Then the second thing that I mentioned is that it doesn't tend to go above about this height. We can understand that too. That's to do with energy. So I give it a certain amount of energy at the start, and over time, because of friction and so on, that energy kind of seeps away. And at any time, if it's got a certain amount of energy, it can't get above a certain point. If it's got lots of energy, it might be able to get all the way up there. If it's only got a tiny amount of energy, then it can only be down here. So as the energy runs down in this thing, increasingly it just cannot it can't get high enough to form a streak going up towards the top of this picture, right? So energy tells us something, and then there's the final thing about it returning to the middle. You can actually see a lot of streaks going towards the middle there. And this one's a bit more subtle. This is something that we call degeneracy in physics. It's basically because if I'm near the middle, there are a lot of ways I can reach it. So imagine if I want the light to be here, then it doesn't really matter where this bit of the pendulum is. It can be over there, and I can still get the light roughly into that position, or it can be up there, and I can still get the light into that position, or it can be, you know, all the way over there, and I can get the light into that position. Near the centre, you've got lots of different ways that the whole thing can be arranged just to get the light into its position. Further out, that's no longer true. If I want the light to be over here, then the only thing I can really do is